All right, so we took some notes about titrations on pages 7 and 8, and in case you missed them or wanted to revisit them, this is a recording of them. And don't worry, this isn't 2 full pages. We're really just finishing 2 last questions at the top of page 8 here in the notes, and it'll be just like what we do at the bottom of that page 7. So if we jump in, what even is a titration? Well, it's a carefully controlled reaction where a standard is used to determine the properties of an unknown. And we purposely built in some words there that we kind of need to decode and make sure we understand, but they mostly kind of sound like what they are. This unknown that we're trying to find the properties of is just a word for a substance we're trying to investigate. There's something that's not known about that substance, and during the course of this experiment, this carefully controlled reaction, we're going to figure out that unknown information. The standard that we're using to do that is just a special solution that we know everything about. So it has a known concentration, and we're going to use a known amount, a known volume of it in our carefully controlled reaction. And the carefully controlled reaction that we're doing is generally going to use this thing that we call a burette, and I'll kind of show you how to spell that later. But this is actually a really specially designed piece of equipment to help us do titrations. Most titrations use these burettes, and there's a couple things about this burette that when you see it in class, you'll instantly kind of understand, oh yeah, that's why we're using this for a carefully controlled experiment. It has this little spigot at the bottom where we can turn that knob in order to control the rate at which we drop chemicals down into the reaction below. We can have it open full throttle where it's just shooting it straight in there and like dumping the chemicals in. We can also adjust it at an angle where it's dropping slowly or dropping quickly, anywhere in between. We can control that very carefully using that spigot. This also is a big, long, skinny tube with lots and lots of lines on it that give us a lot of really good, significant figures. They're even better measuring devices. Those lines are closer together even than a graduated cylinder. So this is going to measure and give us better numbers, better sig figs than we could get with any other measuring device. Now, one thing I want to kind of tell you about this burette is that it's going to have the 0 at the top. Most of the burettes we're going to be using are 50 mil burettes. So they have 0 at the top and the 50 is at the bottom. The first thing you're going to do at the beginning of your experiment is fill the burette up completely up to the 0 line. And the reason 0 is at the top is because these aren't meant to measure how much stuff you put in them. It's made to measure how much stuff is dispensed into the reaction during the course of that carefully controlled reaction. So if it goes down just a little bit, if this is like at the 12-ish line there, then you put 12 milliliters into your reaction. You probably have a lot more than that left in the burette, but that's not what we care about in this carefully controlled reaction. We care how much chemical went into that reaction. Now, this last word, indicator, is a chemical that changes color in specific pH ranges. And so we're going to use that indicator in our lab in order to tell us where to stop in our titration. Because when that pH changes from an acid to a base, then we know we've reached what's called the end point or the equivalence point. And we'll talk more about that special equivalence point a little bit later. But indicators are just special chemicals that change color to help us know when we're kind of done, when we've reached the pH that we're trying to get to. Now, like I said, I'd talk more about some of these special words I've been throwing around. This long tubey thing I've been calling a burette. That's spelled B-U-R-E-T. I'm never going to ask you what's that big, tall, tubey thing that we use in titrations called, but you're going to see that word a lot in our procedure, and we've never used them before, so I want you to recognize that. We're also going to be dispensing chemicals from the burette into the flask. They are Erlenmeyer flasks, but we'll probably just call them flasks. Then there's a big metal rod sticking into a black base that we call the ring stand. And that confuses people because it doesn't necessarily have rings on it, but we can add ring clamps to it if we need to. But we're not going to see any rings this time, but the ring stand is still a big, tall metal thing. And then, of course, since this is a very skinny tube of our burette, we will be using a funnel to help make sure we get all the chemicals into the burette and we don't spill it all over the place. So, not sure how we skipped this quick question, but when neutralized, the reaction, the titration, will be at this thing we call the equivalence point, which is sometimes known as the end point. But the most important thing, and the reason why I'm going to keep using the word equivalence point for the rest of these notes, is that at that special point, the moles of our acid are equal to the moles of our base. That indicator is going to help us indicate when we've reached that point, when that pH is changed, and when they are equal to each other. Now, next question, how does the pH change during a titration? It kind of depends on what situation we have. So I do need you to go ahead and add this kind of general structure into this space. I know there's not a lot of vertical space. We don't need a lot of space here between that first question and this first situation, but I do need you to specify that there are two different situations. The pH will change slightly differently when we add a base to an acid instead of adding an acid to a base. So at the very least, get that adding a base to an acid in here. But I think these little parentheses notes really helps you, especially as beginning chemistry level students. When I say adding a base to an acid, that tells me the acid is what we're starting with, and we're adding base to it, which means the base is in the burette, in the special, tool that we use to add things to our carefully controlled reaction, this titration. So if we're adding the base to the acid, the base is in the burette, the acid is starting in the flask. And if we're adding acid to a base, then the acid is in the burette and the base is in the flask. So just some kind of context for this wording that we're very specific about, because they will be slightly different situations. And the most important thing to realize about these situations is that all of these color changes, when we see that indicator change colors, or when we're graphing the pH like we're going to do down below, it's always focused on what's happening in the flask. Nothing actually changes in the burette except for the level of the chemical. We're just dumping chemicals out of there and it's mixing in the flask. So the flask is where the reaction is happening, where the pH is actually changing. And if we think about if we're adding the base to the acid, if the acid's starting in the flask, and acids have pHs that are less than 7, and bases, the thing we're going to be adding to it, have pHs bigger than 7, then our flask pH is going to start less than 7 and end greater than 7. It's going to be increasing. No matter exactly where it starts under 7 or where it ends over 7, in general, the pH will increase. And if we're adding the acid to the base, we're starting off with that base in our flask. We're going to be starting off with a pH bigger than 7 and slowly adding an acid to it, which is generally going to decrease that pH. The more acid I add, the lower that pH is going to get. Now, this isn't a linear relationship. These tend to be kind of S-shaped curves because at the very beginning of these curves, the pH isn't going to change much, but then it's going to drop very quickly and then level out. Or it's going to be increasing slowly, and then it's going to increase very quickly, and then it's going to level out. So these are always going to be S-shaped curves that we draw. But there's more important than just that general S shape is where that equivalence point is on that graph. So that's what we're going to focus on first anytime we're drawing these graphs. And what we need to think about when we're doing these different situations, because there are 4 different situations that we're going to draw graphs for, and they're each going to be slightly different, is that the acids and bases aren't all the same strength. You'll notice that we have some of those graphs are labeled as strong acid or strong base, weak acid, strong base, weak acid. So there's all different strengths of our acid and the base. And how that changes our graph is going to be that it's kind of like playing tug of war with that equivalence point, with that midpoint of our reaction. If the acid is stronger, it's going to pull that equivalence point onto the acid side of our pH scale and make it less than 7. If the base is stronger than the acid, then it's going to pull that equivalence point onto the base side of things. And if they're equal strength, if they're both strong, like this first graphs that we're going to draw, they're both equally strong, then neither one is going to win, which means that equivalence point is going to be exactly at 7. So that's the first situation that we're going to be drawing. And we're actually going to draw two graphs that are very similar to each other. But the reason we're going to draw two is to deal with those two different situations that we just talked about. How sometimes we might have the acid starting in the flask, and sometimes we're going to have the base starting in the flask. And these are going to look a little different. Even if we mix the same exact chemicals together, whichever one is starting in that flask is going to determine the starting point of our pH on this titration curve. So the first thing, and I already had mine pop up in here, you need to draw the equivalence point before we draw anything else in this curve. And because this is a strong with strong, that equivalence point is going to be at 7. So it should kind of be centered left to right, but that doesn't matter as much as making sure that point is exactly at 7. And if you have to kind of draw a dotted line there in order to kind of make sure it's exactly at 7, you can. Whether you erase it afterwards or not, doesn't really matter. It's not part of our curve, so I'm going to focus on the curve part of things. Now, the next step in drawing a titration curve is to draw a short vertical line centered around that equivalence point. And it is important that it has kind of an equal amount of space, that it goes above the point as below. It should always be centered on that point. We can go ahead and do that on both sides. Try and get it a little more centered. I'm going to shorten this bottom bit a little bit. That looks good for me. So that's always going to have that center vertical area, and the equivalence point is always smack dab in the middle of that vertical section. And here, because we're starting with the acid in the flask, we're going to start our titration curve down in this acid area with our pH less than 7. And like I showed you on the previous slide, we're going to kind of gradually increase this, kind of curve it up to that line that we drew there that's centered around the equivalence point. And then after that equivalence point, we're going to kind of bring it sharply up and then at a shallower and shallower angle until it kind of ends flat there at the end. When we draw the titration curve for the base in our flask, if we're starting with the base in the flask, then the flask pH and our titration's pH is going to start in the base area. So we need to start with our big pH. It's going to start off kind of flat and then curve more and more and more and more as it gets to that equivalence point. And then it's going to keep dropping as we keep adding more acid, drop sharply, and then it'll kind of level off at the end. So notice how these are kind of mirror images of each other here. The titration, it just changes where it's starting and where it's ending, but the general kind of symmetry of it stays the same. And as a reminder, because most of the time I'm not going to be asking you to draw these on a test or a quiz, but I wanted you to kind of have that experience here and see how these things really do change the pH during the titration. When you're looking at one of these titration curves, if we didn't already know and specifically design it to have the acid in the flask, the pH at the start of the graph is always going to tell you what's in the flask. Here, because our pH is starting in the acid area, that means the acid started in the flask. And the pH at the end of our titration, wherever it is always going to tell us what's in the burette. So once again, this ending pH is in the base area. That means the base was in the burette. And the opposite for this. This one, the flask has the base and the burette has the acid. Now there's two more graphs that we're going to draw, but for each of these we're only going to draw one of those variations. All of these graphs we can mirror depending on what's starting in the flask or in the burette. But here, focusing on the fact that this is now a strong acid with a weak base, the acid is stronger, so it's winning the tug of war, which means that equivalence point that in the last two were at 7 now needs to get pulled over onto the acid side of our pH scale. So we're going to pull that down and make it sure it's less than 7. And let's just see, because we started with the acid in the flask last time, let's do these last two as acid in flask as well, just to be consistent so that people don't think when the strength changes that the graph changes too. But just like always, the next step after I get my equivalence point is to draw a little vertical line, however big, however small. Just try and make sure it's kind of centered on that equivalence point. That equivalence point better be lower than 7. And then we're just going to start low because we're starting with the acid in the flask. Try and curve it up. Make sure that we are ending in the base area and we are starting in the acid area. It's not perfect, but it's good enough. With this weak acid mixed with the strong base, because the base is stronger, the base is going to win our tug of war, which means our equivalence point is going to be over 7. And so we can draw this vertical line around that equivalence point. Let's keep it consistent. Like I said, let's keep both of these as starting with the acid in the flask, which means we're still starting in the acid area, maybe just a little bit higher up than we have before. But we could do the same thing, starting from way low down. We just have kind of more of a gradual increase. It looks really stretched out, but I am not going to be asking you to draw these anymore. After this one, we're done drawing curves. You're just going to have to interpret the curves that I draw for you to be able to find this information we've been talking about. So let's go ahead and look at some questions like what you might see on the test. And this is the questions that I put on the review. And I know I have color-coded this a lot because those instructions up at the top of the page or at the top of this section didn't necessarily kind of break things down to the level you probably needed to do the stuff we need to underneath. So I'm going to go ahead and work out this question 32 with you. Not 31. Just real quick, if you don't care about this, you can skip ahead in these notes, but this is the way you're going to have to be asked to interpret these titration curves on tests and, such in the future. So first, we're going to look at the graph, specifically the beginning and ending points of this graph, to figure out if the acid or base started in the flask or in the burette. So remember, the beginning point tells us about what's in the flask, and because that pH is less than 7, that means that we started with the acid in the flask. The ending point pH tells us about what was in the burette, because that's on the base side of things, and because the acid was in the flask, either way, the burette must have the base. Now, the equivalence point is always going to be the point that's in the middle of that vertical section of that S-shaped curve. So this is going to be X. I'm not going to put a lot of points like here, where you have to decide which one is perfectly in the middle, but you do need to be careful about points like W or Y that are kind of close to on that vertical section or at the beginning of that vertical section, but not in the middle. So the equivalence point is always in the middle of that vertical section of the titration curve. So that's point X here. And if we follow point X over to the pH axis, then that pH at the equivalence point is 9. And like we just saw, if our equivalence point is pulled onto the base side of things, which pH 9 is a base, then the base was stronger than our acid when playing that tug of war. So the base must have been strong while the acid is weak. That's it. Quick, easy stuff. Not drawing it, not doing any crazy calculations for it, just looking at given titration curves and being able to analyze and figure out information about the experiment used to make that curve without having to do any chemistry or see anyone doing that reaction. So, jumping down into the calculations that we need to do for the titration calcs. The idea I talked about earlier, we said up above that when neutralized, we're at the equivalence point, which what is equal at the equivalence point? The amount of acid and base. And I'm going to use that idea to start with. You don't have to write this down again. Definitely don't take up that calculation room at the bottom of the page with this. But I want to help derive that MAVA equals MBVB equation, because It seems like kind of random stuff or magical stuff, but it's just coming back to that idea that when our titration is done, or at that equivalence point, the moles of acid are equal to moles of base. They're perfectly neutralized each other. And last unit, we talked about the idea that molarity is equal to moles divided by the volume. And if we rearrange that, we can solve for moles as equal to molarity times volume. And if we substitute the fact that these moles of acid could be equal to the molarity times volume of our acid, and these moles of base is equal to or the same as the molarity times the volume of our base, then we get molarity of acid times volume of acid equals molarity of base times volume of base. Pretty simple extrapolation. Now, something to keep in mind is that on the equation sheet that we use on all our tests and quizzes, we don't actually have an equation MAVA equals MBVB. We only have that same dilution equation that we used last unit, M1V1 equals M2V2. So some students do just kind of use that, the same exact equation. It even works the same in this problem. Technically, there's a reaction going on instead of a dilution, but the process of working out and calculating these answers is exactly the same. So it doesn't matter at all to me whether you call it or use it M1V1 equals M2V2. You know I'm going to give you a little marker if you want to change this equation when you get your equation sheet on the test to having A's and B's instead of 1's and 2's, you can. But I'm going to show you how it doesn't really matter. Mathematically, how we solve this is the same no matter whether it's A's, B's, 1's, or 2's. So the most important thing to remember with this equation is we're always going to be looking for one of these values at a time. And whatever we need to look for, whatever is unknown, is going to be equal to the opposite side of the equation divided by its neighbors. So for example, in these first two calculations, we're going to be solving for MA. And our equation for MA is going to be the entire opposite side of the equation, so that MB times VB still, and then dividing that quantity, once we multiply those together, by whatever was what we're looking for as neighbor. So MA's neighbor is VA. So we're going to be multiplying together the MB and VB, dividing by VA. And the most important, no matter how we rearrange it, no matter what we're looking for, remember that above all, you will always be multiplying together the numbers that are talking about the same solution. So it doesn't even matter if you called it MAVA and divided it by VB. You'd mathematically get the same answer. It doesn't matter what we call them. The math is the same and the answer will be the same. And I won't be looking over your shoulder or at the test to see how you labeled things. I'm just going to be judging you based on how you put those numbers together, the work you do, and the final answer you get. So let's see that in action in this first example. As we read through this, it says that we have a 15.5 milliliter sample of 0.25 molar potassium hydroxide solution. And there's more information there, but I want to point out first, this is the volume of a specific solution. If you're reading through this, can you tell if that potassium hydroxide solution is an acid or a base solution? Technically, it is a base. That hydroxide makes us a base, but that's not really that important for solving this question. But that is why when I label these numbers, this first volume, those milliliters is always volume, I'm going to call it VB. And this molarity we have right after that goes with that VB is what I'm going to call MB, which makes this next number, that fact that we required 31.2 milliliters of aqueous hydrobromic acid. That's our volume, and it's of this acid, that's our VA. And we are calculating the molarity of that acid. We are looking for MA. We know we just solved for that other equation, but I just wanted to reinforce, if you want to use that M1V1, M2V2 equation, that's fine. You would probably call the 15.5 V1, and the M1 that goes with it is important. So as long as that's V1 and M1, and then V2 is 31.2, this will work out the same way. It doesn't matter how you label it or how you look at it. This works fine either way. So I'm going to go back to my A's and B's real quick, just because that's kind of what we do this unit. We're solving for MA. We already talked about opposite over neighbors, got this equation. So as we plug in these numbers, we're multiplying together the MB times the VB and dividing by our VA. If we put that in our calculator, we're going to get 0.10681. And because all of these numbers all had 3 sig figs, we want to round our answer to having 3 sig figs. So that's 0.106, but the 8 is going to round our 6 up. So our final answer is going to be 0.107. And even if we called that V1, M1, and V2, when we solve for the M2, the molarity that goes with that V2, we're still going to be multiplying together M1 times V1 and dividing by V2. So we're doing the exact same math. No matter what you call these things, the math is the same. It's just the A's and B's look a little bit different. So if you're more comfortable with 1s and 2s, go with it. Sometimes that's clearer. You don't have to worry about whether it's an acid or the base. But above all, no matter what you call them, no matter whether you use 1s, 2s, A's, or B's, you need to make sure that these numbers that are talking about the same solution, especially since we have this word of connecting them. I have 15.5 milliliters of this stuff. Those numbers go together every single time. You're going to multiply them together and divide by the third number that doesn't belong with them, that isn't the same solution. So, top of page 8, and I'm actually not going to do this one with you at all. I do want you to try this out. If you don't get 0.0257, then you are probably not getting your volumes in the right place. You've probably switched up your volumes, so double check that. Let me know in class if you have any questions or issues, want me to help you with it. Even with the rounding here, they are all 3 sig fig numbers, so 3 sig figs in our answer. And I want to actually take the time to work out number 3 with you, because this one's a little bit different, and sometimes that throws people off. This one is asking us how many milliliters, so we're going to be looking for a volume this time. We're looking for milliliters of this 1.2 molar potassium hydroxide, which does happen to be our base, so I'm going to call this MB. If you want to call it M1, go for it. And it's asking us, what's the volume required of this potassium hydroxide to neutralize 18 milliliters of 3 molar chloric acid? So that next number, that volume, is the volume of our acid, and this is the molarity of our acid. Even if you start calling these 1s and 2s, you might call this one M1, but then when you see this V here, you can't call this V1. Even though it's the first volume we see, this volume goes with this molarity. So this would need to be V2 and M2, or I guess you could call this first M2 that you're looking for. As long as these belong together and get connected together, they're both 1s, they're both 2s, or they're both A's, or even if you call them VB and MB. It's completely wrong. They're not base numbers. I don't really care, though. The math will turn out the same. The numbers go together. They're talking about the same solution. You're going to be multiplying these numbers together and dividing by 1.20. If I go back to my equation and rearrange it, and keep in mind, if I am solving for VB, which with the way I've labeled things, I am solving for VB, opposite over neighbors is going to be MA times VA, the numbers that go together, getting multiplied together, dividing by the 1.20, as I expected. Now, this answer does come out to be 45. When we look at our sig figs here, this 3.0 has 2 sig figs, this has 4 sig figs, this has 3 sig figs. They don't match at all. Keep in mind, our final answer will always get rounded down to whichever has the least number of sig figs. And the least sig figs we had here was 2, which is actually kind of handy, so we can just leave 45 as our final number answer. Add milliliters, of course, to the end. So, that's it. That's our notes. Now, in class, we didn't spend a whole lot of time working on pages 8 and 9, but just in case we've already gotten past that point and you do need a little bit of help with it, question 1 is pretty straightforward. I know that you might not enjoy writing your neutralization reaction, but hidden in that problem, you have the formula of your acid and base. So that's going to be the first 2 things that you put together, and then you know how to predict the products of neutralization reactions, so you can predict those products and balance it so that we can finish out this page. Molarity is going to be using the same titration equation we've just done and work problems on. question 2 is where the weirdness starts. First off, that neutralization reaction is super weird. I gave you some super weird acids and bases, and I'm so sorry for that. I don't expect you to do a reaction like 2A on your test. No, not going to happen. Just giving it to you, write it down. If you have questions, let me know, and I'll explain it to you. But then this part B, and everywhere else that you see me say hint, use molarity equals moles over liter. So here and here, you're actually going to have to take a little detour before we start using our MAVA equals MBVB. We're not doing titration calculations yet. We're going to have to use the grams in each of those problems, just like I've done here. We're going to start doing a little bit of dimensional analysis using the periodic table's mass to turn those grams into moles, and then we can plug those moles into our molarity equation. Make sure you change your milliliters to liters here. Here it does actually matter that it's milliliters. It won't matter at all later when we're doing our dilution, or it's not a dilution equation, titration equation. So we're going to need to actually solve for this molarity here. And this is technically going to be your molarity of your acid. And notice that we have our volume of our acid and the volume of base used in that titration up above in that original question. So you're going to have to put together these three numbers. Once you are done calculating this molarity, these are the three numbers that you're going to have to combine together to find this problem. And I can help you on it more in class, but that's going to be kind of the exact same process for 3. Write and balance an equation. That one has more normal chemicals. Do this same crazy grams to moles, moles divided by liters, and then you're going to use that answer to help you do the actual titration calculation in part C. So that's all that we did in class, plus a little bit there. Let me know if I can help. Hopefully finishing up this unit with these notes isn't too bad. We only have one unit to go.